force us to compute their fluctuations, and in particular to prove a result of moderate or large deviations. So there will be two parts, and so this morning I will concentrate on the theory, and the examples and applications they will mostly be given this afternoon, so at 2 p.m. I guess. Okay, so so this morning, so this is going to be the theoretic part, and well, I split my talk in 3 parts essentially. So I will start by explaining what is this framework, and well, I will give it a name. So it's a framework of Mod convergence, Mod-Phi convergence. So I will define what it means and well, give some important remarks about the definition. And then I will show, so in this framework, you can show very precise Paris-Sud estimates. So this will be the second part. And from these Paris-Sud estimates, using another technique, you can get large deviations results. So this will be the third part, and actually this is the final goal. This is to obtain large deviation results for these sequences of random variables. Okay, so let's start with this concept of Mod-Phi convergence. So I will fix a sequence of real-valued random variables. So xn, it's a sequence of random variables with value on the real line. And I will assume that the Laplace transforms of these random variables are well defined on a fixed strip of the complex plane. So assumption. The Laplace transform, so the complex Laplace transform, is well defined and so holomorphic on a strip. So let's say SC. So the set of complex numbers with real parts smaller than C in absolute value. Okay, so if you don't, well, you can even assume that C is equal to plus infinity if you really want to be sure that you can apply every possible result. But well, it's sufficient to suffice that you have a well-defined Laplace transform on a strip. Okay, so on a domain that looks like that. Okay, and so the objective is to study the fluctuation of this. Oh, sorry, it's x. Yeah. So the objective is to study the fluctuation of xn, and so we want to compare xn to a large noise, which will be modeled by an infinitely divisible law. So I have to fix a reference law. So we fix also phi. So this is an infinitely divisible law, and that has the same property to have a well-defined Laplace transform on the strip SC. And so we assume that so the Laplace transform of phi, so it's integral of exponential zx phi of dx, is well-defined on SC. And since it is an infinitely divisible law, it can be written as exponential of eta of z, where eta is some function that is holomorphic on SC. And so eta, this is the Levy exponent of my infinitely divisible law. Okay, so maybe I should give 2 examples. So these are, well, the 2 most important examples of infinitely divisible law. So one of them is continuous. If you take eta of z equal to z squared over 2, then phi is a Gaussian law, and it has a density, well, given by the Gaussian. Okay, so phi of dx is 1 over square root of 2 pi exponential minus x squared over 2 dx. Okay, and another example, another possible example is the Poisson law. So eta of z is exponential z minus 1. And then, so phi is a discrete Poisson law, Poisson distribution. And so it is equal to 1 over e and the sum of Dirac at the integers. So in this reference laws, you can have either continuous or discrete distribution. Okay, so now what is Mod-Phi convergence? So I should say Mod-Phi convergence in the complex sense, because I'm going to work with the complex Laplace transforms. So Mod-Phi convergence, it means the following. So we say that Xn converges Mod-Phi with parameters Tn going to plus infinity and limit psi of z, if the following is true. So if, when I look at the Laplace transform of Xn, and I divide by the Laplace transform of phi, but renormalized by Tn, so I multiply by exponential minus Tn eta of z. So let's call this psi n of z. This is a function on the strip SC. This converges locally uniformly to psi of z. And I ask my limit to be, let's say, continuous and equal to 1 when z is equal to 0. So locally uniformly on SC. Okay, so what does it mean? Well, intuitively, it means that your sequence Xn, it is equal to a large noise of size Tn and modeled according to this law phi. And if you subtract this noise, but in the Laplace sense, so if you make this deconvolution of the Laplace transform, what you obtain is a residue that is convergent. So you have a very large noise, and behind you have something that is convergent. And that might be actually the interesting information that you are looking at, that you want to look at. Okay, so intuitively, Xn is a large noise, well, say of type phi and scale Tn, plus some residue that is captured in the Laplace sense by this function psi of z. Okay, and so what we want to do is to compute the fluctuation of Xn, and in particular, we want to compute probabilities like, so the goal is to compute probabilities like, so probability of Xn bigger than Tn of x, Tn times x. So we can expect that a part of this probability will be given just by the Levy, by the infinity divisible law, but maybe there is also psi that is going to come into play, and actually it is the case. So at the end, I will be able to give a formula for these fluctuations, for these probabilities. that depends on phi and on the limit psi. Okay, so before I try to compute these probabilities, what I'm going to do is to make two important remarks. So one of them is on the nature of, well, essentially on the nature of phi. So there are several kinds of infinitely divisible laws, essentially two kinds, non-lattice and lattice laws. So I have to explain that. And another remark that I want to make is that actually, so there are already well-known results that allow us to compute the asymptotics of the logarithm of this probability. So this is given by Ellis-Gartner theorem, for instance. And so I will explain that, and from there we will try to improve this method to obtain actually an equivalent for this probability and not its logarithm. Okay, so the first remark is about the nature of phi and of the exponent eta. So remark number one, so let's say nature of phi. So, so as I was saying, there exist two classes of infinitely divisible laws, and so they are classified by, well, by the nature of the support of the law phi, and also by the behavior of the Fourier transform of phi. So maybe I can start by recalling the Lévy-Khinchine formula. So there is a way to write a theorem that says if you have an infinitely divisible law, then its Fourier transform has the following form. So this is Lévy-Khinchine formula. So if phi is infinitely divisible, then you can write, so if you compute the Fourier transform, so with the previous notation, which is equal to exponential of eta of I psi. Okay, and so this quantity, you can always write it like that. So I m psi minus sigma square psi square over 2, and then an integral over the real line minus the origin of this quantity pi of dx. And here you measure pi, so this is called the Lévy measure of phi. And the only condition on this Lévy measure is that it integrates the minimum of 1 and x squared. Okay, and so for every choice of parameters sigma square m and the Lévy measure, you have a unique infinitely divisible law phi. Okay, so this is the Lévy-Khinchine formula. From there, you can classify, well, you can try to explain what is the support of phi in terms of the support of this Lévy measure. So there are two cases.
So should we think of xn as a cumulative sum?
As
a cumulative sum? Partial sum?
So it can, well, it's not necessarily a sum. It's not necessarily a sum of random variables.
That would make sense why you're assuming this infinitely divisible.
Okay, so yeah, I agree with you. When you take a sum of random variable and you scale it, usually you obtain an infinitely divisible law. But Xn is not necessarily a sum. It can be something more complicated than that. It's not necessarily a sum. It can be a product, or for instance, we have examples where Xn is a determinant of a random matrix, and there it's not at all a sum of anything. Well, it cannot be written in a clever way as a sum of random variables.
The proofs will depend on the infinite divisibility.
So the only thing that we will use actually is, well, the nature of the support of an infinitely divisible law and the fact that the Fourier transform of it, the modulus, in fact, of the Fourier transform of it, and the fact that it doesn't vanish in particular. At some point, it is useful in the proofs. So it doesn't vanish because it's the exponential of something, so it cannot be equal to 0. And this is important at some point.
If we take this equation up here in the definition of mod-phi convergence and take the e to the minus tn eta of z to the other side, should I think of xn as being approximately a convolution of the law under phi and something else?
So that's the point. It's not, so when I say, so I've written intuitively, so it's a noise plus something, but you can, it's not, so for instance, you can imagine that you take another random variable independent y with Laplace transform equal to psi, and then you add a large noise. So this is one of the situations of mode convergence, but actually this is not at all the general case. And well, this case is not very interesting for us. It's sometimes, so you have a very large noise and you cannot subtract the noise. You don't have a random variable behind, you just have something in the sense of Laplace transform, so of deconvolution of Laplace transforms. Okay, so let me continue. So as I was saying, so there are two cases. So case number one. So in this decomposition, you assume that sigma square is equal to 0. Okay, and also that, so you introduce the shift parameter. This is m minus the integral of x over 1 plus x squared against the Levy measure. And you suppose that this is, so that this is well-defined and finite. Okay, and there is a third assumption. You also assume that pi doesn't charge a neighborhood of 0. So there is some epsilon such that pi of minus epsilon is equal to 0. Okay, so if this is the case, then the support of phi, so the support of a measure is the smallest closed subset such that, which has probability 1 under this measure. So in this case, the support of phi, it is equal to gamma plus, and so you take the closure of the semi-group generated by the support of the Levy measure. Okay, so you take your Levy measure, you take its support, you take any possible sum of elements in this support, and you add gamma, and you will obtain the support of phi. This is the first case. And the case number two, well, in any other, so if this is not true, for instance, if sigma square is not equal to 0, or if gamma is not finite, or well, not well defined, the support of phi is equal either to R or an half line. So something like gamma plus infinity. Or, well, the opposite, minus infinity gamma. Okay. And there is a way, actually, in terms of the Fourier transform, to characterize these two cases. So let me, well, maybe I can write it as a proposition. So if you are in case 1, so you are not necessarily a lattice distribution, but you have to look at this, well, at the group generated by the support of phi. If, so let's write it Z, of the support of pi is a discrete subgroup of R. Then one says that phi is a lattice distribution. Okay, and so up to scaling, we can always assume that this subgroup is included into the group of integers. So up to a renormalization one can assume that this group is included into Z. And then, in particular, the support of phi is included into Z. Okay, and so in this case, the Fourier transform, its modulus is equal to 1 if and only if the argument is in the lattice 2 pi of Z. So phi of exponential I psi x equal to 1 if and only if psi belongs to 2 pi Z. Okay, and in any other case, so you are called non-lattice distribution. So this can be in case number 2, or if you don't have, this is not a discrete subgroup of R. And then the Fourier transform, it is always strictly smaller than 1, except when psi is equal to 0. So otherwise, so this is a case of so-called non-lattice distributions. So the support of phi is not a lattice. And this is characterized by the fact that phi of exponential I psi x in modulus is strictly smaller than 1 for every psi different from 0. Okay, so when you have when you have an infinity divisible law, so it can be supported on a lattice, and this is characterized by this condition on the Fourier transform. And otherwise, you call this a non-lattice distribution, and you have this. So for instance, in my two examples, where the first case was a non-lattice distribution, and the second case was a lattice distribution. And so what I'm going to do is I'm going only to work with non-lattice distributions, and at the end, I will explain how to deal with lattice distributions. So it's, well, you can use essentially the same argument. Well, there are small modifications, and the result, there is a small modification in the formula for this probability, for instance. So I'm only going to use infinity divisible law with this property, so that are non-lattice distributions. Okay. So this was my first remark, and there is a second remark. So it's what was known before in order to compute this the logarithm of this probability. So the remark number 2. So if you look at the logarithm of the Laplace transform, so let's take it with parameter t that is real, and if I divide this by tn, this converges under the assumption of mod convergence to eta of t. Okay, in this setting, you can apply what is known as Ellis-Gartner theorem. So Ellis-Gartner theorem, it tells you that you can compute the logarithm of the probability, or the asymptotics of the logarithm of this probability in terms of the Legendre-Fenchel transform of this Lévy exponent. So one can compute the asymptotics of logarithm of this probability divided by Tn. So it involves the Legendre-Fenchel Laplace the Legendre-Fenchel transform of eta. So let me recall what it is. So the Legendre-Fenchel transform of eta. So eta is a convex function because its derivative is given by variances of random variables, so it's convex. So it is defined like that. So it's a function f of x, which is the supremum over all h of hx minus eta of h. And by taking h equal to 0, you can check that this is, so with h equal to 0, you obtain 0, so this is always positive. So it is always positive, and it is a convex function, and so the, so it's a convex function. And it is useful to know that the h that maximizes this quantity, well, it is given by a very simple equation, which is eta prime of h is equal to x for the maximizer. Okay, so Ellis-Getzner theorem, it tells you that, so let's say for every x strictly bigger than eta prime of 0, you have this is asymptotic. And if x is smaller than eta prime of 0, well, you have the same thing with xn smaller than Tn of x. Okay, so what we want to do is, so what it means is that, so if I look at this one, it means that your probability of xn being bigger than Tn times x, this is equal to, well, so you have an exponential term, exponential minus Tn f of x, and then you have something else which is not of exponential, which is not of exponential decay, so you have a term Rn of x. And so Rn of x is not something that decays like an exponential in Tn. It's something, well, larger than that. And so what we want to do is compute this quantity. The question is, what is this quantity? And so, for instance, in the case of mod Gaussian convergence, so f of x is, in fact, it is x squared over 2, so it tells you that you have Gaussian tails. And what you want to do is to compute this remainder to see if your Gaussian tail is really Gaussian or if there is something else. And we'll see that actually there is something else that involves the factor psi in the definition of mod convergence. So this is what we do. What we will do at the end of the talk. Okay. So after these two remarks, so I can go to section 2. So I'm going to prove that if you have Mod-Phi convergence with a non-lattice distribution, then you have a very, well, then you have, in any case, a very SN estimate. So there is a renormalization of xn that converge in distribution to a Gaussian law, and you can compute the Kolmogorov distance between the two distributions. Okay. So various SN estimates. So the assumptions for these sections are the following, and they will be the same for the third part. So I fix again a sequence of random variables, xn, and I assume that it converts mod-phi with parameter Tn going to infinity. Okay, and I assume phi to be non-lattice, so this will be a non-lattice distribution. Also non-lattice infinity divisible law. So in particular, what this means in terms of the Fourier transform is that this is strictly smaller than 1 for psi non-zero. Okay. And so with parameters Tn and limit psi. And all of these quantities, so psi and the Laplace transform of xn and phi, they are defined on the strip SC. Okay, so the theorem is the following. So I will introduce a normalization of xn, yn, so it's xn minus Tn theta prime of 0, and divided by square root of Tn theta second of 0. Okay? And I denote Fn, this is a cumulative distribution function for Yn. Okay, so the theorem says that Fn of S, well, this is almost equal to a Gaussian, so you can write it as the integral between minus infinity and S of the Gaussian distribution, so d of y, this is 1 over square root of 2 pi exponential minus y squared over 2. And okay, so this is not really true. You will have 1 plus something small. So the small thing will be something like that. So psi prime of 0 y divided by square root of Tn theta second of 0. And there is also something that depends on eta. Okay, plus a remainder that is a small o of 1 over square root of Tn. And this quantity is uniform over the real line. So this is the important part. Uniform on the real line. So this is valid for any S in the real line. Okay, so I'm going to prove this theorem. Before that, so why do we need such variation estimates? So we want to have a better version of Ellis-Gärtner theorem. And if you look at the proof of Ellis-Gärtner theorem, so you can find it, for instance, in the book by Dembo and Zaitoni. So what is done is that first you have to prove that xn over Tn goes to eta prime of 0. So this is some kind of law of large numbers. And then once you know that, you use an argument of tilting. So it's something like you have to do a change of variable on xn to compute probabilities like that. So you replace these probabilities by probabilities that depend on the new random variables that are obtained by an exponential, in fact, change of measure. So and this will only give you estimate of the logarithm of the probability. But so what you can imagine is that if you have something better than this law of large numbers, if you have something more precise, so let's say a central limit theorem, then you will obtain something more precise here. So in fact, an estimate of the probability instead of its logarithm, and so an estimate of this remainder Rn of x. So this is exactly why these variation estimates are important. Okay, so now let's prove the variation estimates. So for the proof, I will use a lemma that I will just admit, and I will give adequate references. And it's actually a lemma that is used in the classical Gaussian estimates for some of RID random variables, and that appears, for instance, in the book by Feller. Okay, so the lemma is the following. And so you can find it in, for instance, in the book by Feller, Introduction to Probability Theory and its Applications. And so it's in the second volume, and I guess chapter 15 or something like that. Okay, so the lemma says the following. So it's a way to compute the Kolmogorov distance between two distributions in terms of the difference between their Fourier transform. And since we have even better than Fourier transform, we have Laplace transforms, this is going to be very useful here. So the lemma says, so you can state it for a pair of arbitrary random variables. So let's take, so y and z random variables. And I will introduce their cumulative distribution functions. So fy of s, which I write as an integral. So this is the probability that y is smaller than s. And similarly, the cumulative distribution function of z, I write it as an integral. So the function, so here f of y, it's, well, it can be a function, it can even be a distribution. It's just a notation if you want. Okay, so there is a way to compute the Kolmogorov distance between y and z in terms of the Fourier transform of f and g. So it's the following thing. So the supremum over s of the difference between the cumulative distribution functions. So it is smaller than some integral which involves the Fourier transform of f and of g. And you take it over an interval of size 2t, so well, of size t. And there is a remainder, which is 24 times, so you take the supremum norm of g and divide it by pi times t. Okay, so we just admit this lemma. So in short, it tells you that if you can control over an interval of size t the difference between the Fourier transform of two distributions, then their Kolmogorov distance, it will be of order big O of 1 over t, because here you have this 1 over t. So in short, this is what is the content of this inequality. Okay, so once we have that, well, we're going to apply this result with y equal to yn, so to xn minus tn eta prime of 0 divided by square root of tn. And to z, that is, well, almost a Gaussian. So a Gaussian, modified by this factors. So I will take, so y is yn, and I have to compute the Fourier transform of yn. So what is it? Okay, so I use the definition of yn. Okay, so what I have here, so I have something that is constant, and then the Fourier transform of xn with argument psi divided by square root of tn. So this is equal to, by this, sorry?
Give it double prime.
Oh yeah, sorry. Yeah. This was missing. So this is equal to, by definition of mod convergence, okay, so psi n, this was my residue that is going to converge to psi. And then there is also exponential minus square root of Tn. So it's also this quantity. Okay, so this is going to converge to psi, and it's also true for the derivatives because you have a holomorphic function. So this quantity, you can approximate it by, so psi of 0, this is 1. And then there will be psi prime of 0 times this, and a small o of psi divided by square root of Tn. Okay? And for the other terms, so you have Tn times eta minus its first derivative, in fact. And so what you obtain is the second, then you can use the second derivative. So for these terms, here, what you obtain is exponential, so this, in fact, and there is a, so if you want to control the remainder, so you have 1 plus, and you have to use the third derivative at 0 of eta. And a small o of psi power 3 divided by square root of T. Well, I should, okay, maybe I should write it like that. Okay. So if I take everything and put it together, so I obtain exponential minus psi square over 2. And then I have 1 plus smaller terms, so this one. This one, eta third. And then, so what remains is 1 plus psi square times this small o of psi divided by square root of Tn. Plus. Okay. So we have computed well, the asymptotics of this Fourier transform. So this is my f of f hat of psi. Okay, and so for my variable z, I will take well exactly the same Fourier transform, but for this remainder that I will just remove. So z will be defined in fact in terms of its Fourier transform. So to define z, well, so Zn, I take G hat to be equal to the same thing, but minus the remainder small o of psi divided by square root of Tn. One. Okay, and if you have this Fourier transform, it's easy to compute the inverse Fourier transform, so the density G of Y. So it's given by the Gaussian. And then, so these terms, they transform into 1 plus psi prime of 0 y divided by square root of Tn, theta second of 0. And this term here it gives you y squared minus 3 times y. So this is just a computation. You just do again a Fourier transform to obtain g of y. Okay, so I want to compute the Kolmogorov distance between these two things, and to prove that it is a small o of 1 over square root of Tn, because this is exactly the content of the theorem. So I apply my lemma. So what I will do, so I will take T equal to delta square root of Tn. And well, for the computation, I will also need to fix a small delta. And at the end, I will make this large delta go to plus infinity and this small delta go to 0. But so for the moment, these quantities are fixed. Okay, so I take T like that, and I will split my integral in two parts. So first, I have this term. So this entity it is bounded because you have a Gaussian multiplied by a polynomial, so of course it is bounded. So the Kolmogorov distance between Yn and the L, so it is smaller than, so you have this 24, the density. No, there is no square root. Okay, and so then I want to split my integral in two parts. So there is 1 over phi, and I take the integral between minus small delta square root of Tn and plus delta square root of Tn. Okay, and so what do I have? So I subtract this with this. So what I obtain is okay, so if you look at this, in fact, this is just a small o of 1 square root of Tn, a small o of 1 over square root of Tn. Because you can write this as 1 over square root of Tn times something that is small, that depends on eta and that goes to 0. Okay, so this will be a small o of 1 over square root of Tn when delta goes to 0. Okay, and there is a other part of the integral, so I integrate this time over this union of two intervals. And so what do I have? So I have my, okay. So something like that. here I have 1 over square root of okay, so here this delta square root of Tn comes from the 1 over psi that is over there. Okay, if you integrate over an interval that doesn't include this small interval, then you can bound 1 over psi by 1 over delta square root of Tn. So I claim that this thing, in fact, it goes to 0 much faster than any power of Tn. And why is that? Well, so if you look, for instance, at this Fourier transform, you can see that its modulus, so it is equal to exponential eta so the modulus of this quantity is equal to that. Okay, so this is bounded because my function psi, so I take it over an interval small delta, big delta, and this is smaller than a constant that depends on delta for this part. Okay, and so, yeah, I've forgotten something. Here there is a Tn. This quantity here, so here we use the fact that we have a non-lattice distribution. The maximum of this function over this interval, this is strictly smaller than 1. So this is something, well, that depends on my parameters, but that you can bound by Q delta and delta to the Tn, in fact, with this strictly smaller than 1. Okay, so you have something strictly smaller than 1 to the Tn, so it goes to 0 much faster than any power of Tn. So the second interval, in fact, it is a small o of 1 over square root of Tn and even of any power of Tn. Okay, so now we are done because so now I can make delta go to 0 and this will be a small o of 1 over square root of Tn. And I can take this quantity go to plus infinity, and again this is a small o of 1 over square root of Tn. Okay, so the end of the proof, you take delta as small as possible, and the delta goes to plus infinity, and you're done. Okay. So so maybe I should say something about these various SN estimates. So so for instance, if you use it in the case of mod Gaussian convergence, so by that I mean that phi is a Gaussian. So in this case, there is no term like that because eta, the third derivative of eta is equal to 0. So there is only this quantity. And so it tells you that the Kolmogorov distance between your scaled random variable and your Gaussian law, the Kolmogorov distance is of order big O of 1 over square root of Tn if this derivative is not equal to 0. So maybe I can make it a theorem. Oh, well, remark. So the remark is that if you take, for instance, phi equal to a Gaussian, so it is a non-lattice infinitely divisible distribution, so what you obtain is that the Kolmogorov distance between xn over square root of Tn, and your Gaussian is a big O of the first derivative of psi at 0 divided by square root of Tn. So this is good unless psi prime of 0 is equal to 0. Actually, there are many situations where psi prime of 0 is equal to 0. So this estimate, so this variation estimate, it is actually only useful in order, it's not useful as a variation estimate, but only in order to prove after that the large deviation result. If you want precise variation estimates, you have to be more careful, in particular if psi prime of 0 is equal to 0. So this is good, unless psi prime of 0 is equal to 0. And so in this case, so you can still use a framework of mode convergence to prove optimal variation estimates, but you have to be much more careful. And you have to choose your parameter t, for instance, in a different way. Okay, so now we can go to large deviation estimates and well, state the main result. So do that here. Okay, so the assumptions are the same as in section 2. So the same as for variation estimates. So in particular, phi is again a non-lattice distribution. So maybe I should write it. Phi is non-lattice. And the theorem well, tells you what is the asymptotics of the probability that xn is bigger than tnx. So here there is a restriction on x, so you want x to be bigger than the, well, than the mean of xn, so which is proportional to eta prime of 0, and also to be smaller than eta prime of c, so where c is the parameter, the size of the strip of convergence. So in many situations, in fact, c is equal to plus infinity, and so you don't have this restriction, but I just want to be very precise. So this probability, it will be equal to the following. So we know that there is something like that, right? And now the remainder, so there is a square root of 2 pi tn eta second of h also here, and psi of x. Sorry, psi of h. Okay, and h, so again, it is given by the equation eta prime of h is equal to x. And 1 plus small o of 1. And this small o is uniform if you take x in a compact set. So let's say locally uniform. So what this tells you is that, so for instance, if you do it with a Gaussian, f of x, it will be x squared over 2. Here you won't have this term. So it tells you that your probability, the probability of the fluctuations at order Tn for Xn, they are given by, so this will be in fact the Gaussian tail, but then multiplied by a factor psi of h, which is not necessarily equal to 1, which might be equal to, which is psi of h, so not equal to 1. So you have to multiply your Gaussian tail by an additional factor. Okay, so this is for x bigger than eta prime of 0. And in the other situation, where you have, you just have to make a change of sign, so to look at minus xn. So if x is strictly smaller than eta prime of 0, then you have the same kind of asymptotics, you just have to be careful. So this means that h, in fact, is negative. And since it is negative, here you have to take the absolute value of h. But otherwise, this is the same problem. Okay, so let's prove this. So the proof uses a tilting argument, well, exactly as in the proof of the Ellis-Gartner theorem. And then we're going to use the Bayesian estimates. Okay, so the proof starts again with an important lemma that I'm going to prove. So I suppose that I have xn that converge mod phi with parameter tn on the side. And I will make a change of measure, so I will introduce xn tilde. So I take h, let's say positive, and again, so theta prime of h. No, I just take h positive. Okay, and so I define a new random variable with the following probability. So the probability of xn tilde, it is given by exponential h times y. And so I will have to divide by the experience of exponential h xn. And so this is a chain of probabilities. So exponential chain of probabilities. So I claim that my new sequence xn tilde, it also converges mod phi tilde with a new infinity divisible law, and with parameter tn and some new function psi. So xn tilde, it converges mod, so this function and with parameter, sorry, this is, it doesn't mean, okay, so here we just use the Levy exponent. And so the new Levy exponent is the following. Okay, so again with parameter tn and with limit, which is a function, so again, psi of x plus h divided by psi of h. Okay, and so why is that? Well, it's easy. We just have to compute the Laplace transform of xn tilde. So indeed, if I compute this quantity, so this is equal to this shifted Laplace transform divided by the Laplace transform at h. Okay, and so by definition, this is equal to, well, by assumption of mode convergence, this is equal to this. Multiplied by psi n of z plus h divided by psi n of h. Okay, and this converges to this limit. And this is what is written here. Okay, so when you make an exponential change of measures on a mode convergent sequence, you again obtain a mode convergent sequence. You just have to change the reference law and the limits, and the parameter tn are the same. Okay, so once we know that, so what we're going to do, in fact, is to use the Bayesian estimates but for xn tilde. Okay, so maybe it's useful to introduce then yn tilde. Okay, so this satisfies CLT with very SN estimates given, given by this theorem. Only here you will have psi prime of h, I guess, and maybe here eta third of h. So you will replace 0 by h everywhere, but otherwise this is the same theorem. So satisfies the CLT with very SN estimates. Okay, and so this means that the cumulative distribution function of yn tilde will be able to replace it by the one of a Gaussian. And once I know that, so maybe it's useful to keep this result. So that is just a computation, in fact. So if I want to compute this probability, so I will fix h, so take h given by the equation eta prime of h is equal to x. So this means that this is h that allows you to compute the Legendre function transform f of x. So I want to compute this probability. Okay, so by definition, of course, it's integral is equal to this integral. And I will replace this by an integral with respect to the new probability measure. So I obtain hxn. Okay, I just replace the probability here by its value in terms of xn tilde. Okay, and if I know I can use this scaling, so write it in terms of yn tilde. So what I obtain is okay, so I obtain this. I have also shifted, well, so make a change of variable to start from 0 instead of this tn of eta prime h. Okay, and so if you you can write this actually like that. So this quantity, this is exponential tn eta of h. So it's also a tn, so minus h tn eta prime of h. So I will put it here. Okay, and then the same integral. Okay, so if you look here, you have eta of h minus minus xh. So this is exactly minus f of x. Okay, and here what you do, so you are integrating something that is well smaller than 1 against the probability measure. So it's, okay, I'm just going to say that you can replace this by the Gaussian up to a factor small o of, well, small o of 1. So here, this one, in fact, is just equal to the same thing, but with the Gaussian distribution. Because of the Bayesian estimates. Minus y squared over 2 dy. Okay, and if you compute the, also I think I have forgotten something. Oh, sorry. So here I have forgotten a psi of h. Well, psi L of h. Okay, so which will become psi of h as n goes to infinity. And so, and this integral here, you can compute it, so it's asymptotics, it's just, so it's a Laplace method. It is given by that, up to remainder 1 plus small o of 1. Okay, and there you have everything to obtain the formula, so this formula. Okay, so I will, well, end this theoretical part by, again, 2 remarks. So, the first remark is that in this case, what you obtain is fact, so you have the fluctuations of order at order Tn, and you also have the fluctuations of order square root of Tn because they are given by the Bayesian estimate, so they're just given by the CLT. And so in fact, what is true is that you can describe all the fluctuations between Tn and, well, between square root of Tn and Tn. So I'd like to do the following scheme. So it's a kind of panorama of every kind of fluctuations that you have between scale square root of Tn and Tn. So let's do it here. So if you look, so this will stand for the fluctuations, well, the order of fluctuations. Of XL. Okay, so if you look at order dgo of Tn to the 1/2, what you know is that the probability that Xn minus okay, that Xn is bigger than Tn eta prime of 0 plus square root of Tn eta second of 0 times y. This is the same as the same probability but with a Gaussian. Up to 1 plus small o of 1. Okay, so this is the CLT. And you even know what is the difference between this quantity and this quantity, so you have various estimates. Okay, and so on the other end, at the order dgo of Tn, so you have the probability that Xn is bigger than Tnx. So this times this term, I will just put the letter x. And so this is strictly smaller than eta prime of 0. So it is given by a term, in fact, that looks like what is given by the central limit theorem. There's a Tn, you see. But modified by a factor psi of h. Okay, so you are in the regime of, well, at least moderate deviations or large deviations. So let's say large deviations. And so now you might ask what happens in between. So to really see what happens in between, you have to make an extra assumption. So before I was assuming that phi is a non-lattice law. So it doesn't mean that it is So it's a bit difficult, but it doesn't mean that it is absolutely continuous with respect to Lebesgue measure. It can be supported on something very very messy, like I don't know, a Cantor set or something like that. So not a discrete lattice, but something very messy. So in order to really have the full panorama of fluctuations, so you have to assume that phi is absolutely continuous with respect to Lebesgue measure. And so it's not very easy to characterize in which case this happens, but you have sufficient conditions. So for instance, if your parameter sigma square is positive, then this is the case. So, for instance, sigma square strictly positive. And there is also another sufficient condition in terms of the Levy measure. So if the Levy measure, has a sufficiently big, absolutely continuous part, then this is also the case. So if this is true, then in fact you can show that so there is an intermediate scale, big O of square root of Tn to the 2/3. So if you look at these probabilities, so this time I write them like that. And so if I want fluctuations, so at scale big O of Tn to the 2/3, y is of order Tn to the 1/6, for instance. So this is given by exponential, so the same formula, but without the term psi of h. Okay, and so what happens is the following. So this formula is valid between this order and up to small O of Tn. So I should put an arrow here. And at order big O of Tn, there is this additional term psi of h that appears. Okay, so you know what happens between this scale and this scale. Okay, and between this scale and this scale, in fact, we can use, well, this formula, it degenerates to just the probability of the Gaussian term. So this formula, in fact, it is valid from big O of Tn to the 1/2 up to small O of Tn to the 2/3. Okay, so maybe I should use colors. So this formula it is valid in this scale. Okay. And this one, so for this one you need the additional assumption. It is valid over there. And then the third formula, so the large deviation, it is valid at scale big O of Tn. Okay, so this was the first remark. And there is another remark. So I told you at the beginning that I was going to tell you what happens if I take a lattice distribution this time, so something like a Poisson law. So actually everything stays true. You only have to replace this h here by something else. So in the lattice case, same formulas, but you have to replace, one needs to replace so this factor 1 over h here by 1 over 1 minus exponential minus h. Okay, and so the reason for that is that, so the Fourier transform of the reference law phi, its modulus, it is equal to 1 at some point, which was not the case for non-lattice distribution, and it is equal to 1 at some points that are given by a lattice. So you have to add a series that in fact is given by this quantity, and that replaces this 1 over h. But otherwise, you can essentially do the same kind of asymptotic analysis. So the same formulas, but you just have to replace this factor by this factor. So maybe you can see that if you take h going to 0, these two things are equivalent. Okay, so so this afternoon in particular, I will give some example in the lattice case, and I will use this factor. So I've not shown you how to obtain this factor, but I'll tell you this is true. You can do the same kind of things. Okay, so maybe to give you yes.
So maybe you can relate to what I said last week. Your scheme in the case of Mod-Phi.
So you mean that you wanted to write it with a Gaussian? Okay, so if you have a Gaussian, so f of x is equal to x squared. So in this case, actually, this probability is the same as this one. So it means that you have a central limit theorem between this scale and this scale. So the reunion of the red and the yellow part. So this is given again by Gaussian test. And you start to see something that is not Gaussian at scale big O of Tn. And so this is for the Gaussian case. And in the non-Gaussian term, when you have something a bit different. So this is not really Gaussian, but yeah. Just to tell you what I'm going to do this afternoon. So I'm going now to study examples. So once we have this result, so we can really use them as a black box to obtain moderate or large deviations. But what we need to do now is to compute the asymptotics of the Laplace transform. So we need to have tools to compute the asymptotics of this Laplace transform. In particular, we want to have a theorem that tells you, okay, this is equal, for instance, to exponential minus Tn this square over 2, so this is a Gaussian term, times something that is convergent. Okay, and the question is, when can one write something like that? So I'm going to try to give you some results about this. So it's easy to obtain a result like that if you know how to compute this thing, and this thing is easy to compute if Xn, for instance, is a sum of independent random variables, because you just have a product and, well, you have an infinite product and you do its asymptotic analysis. But this technique, it fails when Xn, for instance, is a sum of dependent random variables. And so we have developed well, a framework, a new framework to well, still to obtain this kind of asymptotics. So we start with independent random variables, and well, at the end we will have removed this hypothesis actually, and we will be able to look at some of random variables with any structure of dependency. Okay, thanks. So it's at 2 p.m., right?